Hi everyone, today we're going to continue our analysis on refrigeration cycles. Last time we talked about part A, but I forgot to draw the TS diagram, so we're just going to do that real quick. So if we have our TS diagram here, and we know that at state 1 it's a saturated vapor, so that's when the quality is equal to 1, so it's going to be somewhere here. Okay, so this is x equals to 1 right here. So this is our state 1. And we know that state 2, from state 1 to 2 is isentropic, so it's going to be a straight line because delta S is equal to 0. And also we start with T low equals to 0 degrees Celsius, and we're going to go to a higher temperature reservoir. That means the temperature is going to increase. So we're going to draw a straight line going up, so something like this. And this is going to be our state 2. Okay, so that's the last part of part A. And today we're going to focus on part B. So part B, what is the mass flow of the refrigerant through the compressor if it takes 1,000 watts of power to run the compressor in the ideal case? So we know that the W dot is 1,000 watts, which is also 1 kilojoule per second. We're going to convert this unit because it's going to be consistent with other units throughout the problem. So in this problem, we're going to use the our steady flow energy equation. Steady flow energy equation. So for a compressor, so that is m dot delta H is equal to negative W dot. So if we want to find the mass flow rate, m dot, that is just W dot negative W dot over delta H. So next step, we're going to find our H's. So it's negative W dot over H2 minus H1. If you recall from the previous video, we know that at state 1, x is equal to 1 and the temperature is 0 degrees Celsius. So if we just go to table A.1, we can find that H1 is equal to Hg is 398.6 kilojoule per kgk. Kilojoule per kg. kgk is for entropy, sorry. So it's just kilojoule per kilogram. Okay, so this is H1. Now we're going to find, so this is for state 1, and now we're going to find H2. Similarly to how we found our T2 for part A, we're going to use interpolation to find H2. Because if you go to table A.3k, there is no exact value for state 2, so we're going to interpolate. So we're going to have something similar. So I'm going to draw this table again. So we're going to have our S, so 1.7175 and 1.7455. So this is the first row, this is the third row, or the second row in the table. And then we know the H is 4.41057 and 418.96. So this is the value that we're looking for, H2. And we know S2 is from part A is 1.7271. Okay, so if you don't remember this, it's just S2 is equal to S1 is equal to 1.7271. You can also refer back to our previous video. Okay, so we're going to do our interpolation here. So H2 is equal to S2 minus S1 over S3 minus S1 times H3 minus H1 plus H1. And that gives us our H2, which is 13.45 kilojoule per kg. Okay, so now we know H1 and H2. We can plug in to our steady flow energy equation. So it's just -1. Remember, we already convert the unit earlier, so we can just directly plug in our values for 13.45 minus 398.6, and this will give us the mass flow rate, which is 0.0673 kilogram per second. Alright, so this is part B. Let me know if you have any questions or feedback. And next video we're going to talk about part C. Thank you.